Hello, fellow NEEP instructors. Today's lesson is going to be the kinesthetic learning style, where we will have audio and visual and interactive learning of this series parallel circuit that we're going to go through together. So, with no further ado, come on in, let's go. So today we're going to go to this one is going to be the DC circuit challenge right there. Let's see if we can get that to load up. And then we're going to come on in and get the series parallel number 5. And we're going to begin learning this circuit right here. And let's go. Come on, guys. So we are going to start out by drawing the circuit over here with the power supply like that. And let's go with, all right. There and a point here with a resistor and a resistor. Come down back around to the power supply with a resistor here, another point, and we're going to call this R1, R2, R3, R4. I'm going to try to provide my use of the matrix on how to solve this problem. And what they've given us was the current value across R1. So this is provided 5.088 milliamps. 5.088 milliamps is provided. Also 10.32 volts. 10.32 volts. And also provided is 560 ohms on R2. R3 is 1,000 ohms. And R4 is 560 ohms. Okay, so this is the values that were given. The resistance across R1 is not given, but with this matrix chart of organizing, we are going to plug in the values that we know. All right, so maybe one part of an interactive learning style would be able to sing a song. Yay, I love doing parallel circuits mixed with series. La 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 la. La 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 la. So here we go. They gave us the 10.32 volts. And they gave us the amps flowing across there. And we're going to call this 0.005088 amps. Okay. And I just reduced the milliamps into full amps by adding the 2 zeros. That way it gives us a number that we can use on our calculator to do some easy math. They did not give us the resistance across R1 or the voltage. So we know that the resistance in R1 is going to be the resistance of the current coming out of the circuit going into the circuit is going to be the same. So we know our total amps would be that. All right. Now, what else can we find out? Well, we know that this is our Ohm's law. Right, and so this is a multiplication problem, and this is a division problem, right? Voltage, current, resistance. And if you give me 2, I can figure out the third. So I have voltage, which is E, and we can take that into our calculator here. And we can plug it in. It says 10.32 divided by 0.005088 equals, I got 2,028 ohms total circuit. So here we are. If that's the case, and I have a value on this chart here that says what is my total resistance, and if I want to check to see if my progress is correct, right here on this computer we can plug in the values of 2028 and check this as a corrective, and it tells me we're on the right track. So we can keep plugging in and let's see how we're doing. So what does this mean? So the values of the resistors across R2 is my resistance there is 560 ohms. R4 is also, oh, I'm sorry, we don't know this one yet, but R2, 560 ohms. R3 is 1,000 ohms, and R4 is 560 ohms. And we can take this and start to plug in some values, right? So what do we know? We don't know any two things to get the third. So how are we going to find out where to start? Well, we have the total resistance. If we know the total resistance, we know what these resistors offer to the circuit. So we know R2 and R4 are in series with each other. Those two series resistors would be 560 and 560 is going to give us 1,120 ohms. These two resistors are in parallel with this. So there is the product over the sum that says R times R over R plus R. So if there's two, this is going to be one. This is 1 and 2. So we're going to use these two resistors. We're just going to make this one resistor because these two are in series with each other. So we're going to say 1120 times 1,000 over 1120 plus 1,000. So let's go do that. 1120 times 1,000 is going to equal 1,120,000. And then we're going to take this and just divide it by, that's going to be 2,120. So let's just go divided by 2,120 equals. So this is 528. So this equals 528. So if this is 528, this total resistance is 528. So we're going to take this 528 and subtract it from 2028. So we're going to go 28, 528. So it looks like this is going to give us probably about 1,500. So that being said, this is the resistance that's left over from calculating the total resistance and subtracting the resistance that's in this circuit here, which would show us that we had 1,500 ohms here. Okay. And checking to see if we're correct, we can go with our math now that we said 1,500 ohms. It's a good round number. We can go current times resistance, 0.005088 times 1500 equals, that's 7.632. 7.632 volts. And we can check our voltage drop across R1 right here and plug it in. 7.632. See if we're correct. And we are on the right track, guys. Woohoo! All right. So, you guys with me? All right, here we are. So if I got 7.632 dropped across R1, this is really helping me organize my thoughts now. So I have to know what's left over. So what's 10.32, my total voltage, subtracting the voltage that's dropped across R1, minus 7.632 equals, so I got 2.688 volts left. It's going to be right there. The rules for a parallel circuit said the voltage remains the same across a parallel circuit, guys, right? All right, obey the law. So the voltage dropping across R3 is going to be 2.688 volts. All right. So, is the same voltage going to be across here and here? No, those are resistors that are in series with each other, so they'll drop proportion to their resistance. So, we have 2 here. We can plug in the third value. So, we know 2.688 divided by 1,000 equals.
The number was off on that.
Well, let's see. Let's double check that right there. Here we are. We're going to go 2.688 divided by 1,000 equals. We're going to say this is 0.00268 amps. And I've tried to work with this program before and reduce these numbers down just the little ones, and I end up getting these numbers wrong. They're very sensitive on this program. So I just learned to write out whatever it expects, give it what it wants, and I've had better success than rounding stuff up and down. So let's go and let's figure out what's going on with here. So if I have basically if I got the 2 milliamps flowing through right here, whatever is left over is going to be flowing through here, right? Because that's what's left. So we're going to take a big number of 0.05088, subtract 0.00268 equals 0.0024 amps. 0.024 amps. That's what's left over. And whatever's left over has to be flowing through this portion of it. 0.0024 amps. And of course, we make these milliamps by going 1, 2, 3 places over to the right. So, that being said, I can now figure out what the voltage drops across these 2 resistors are based on the following the laws, applying them as we see them in the circuit, and just doing Ohm's law across the matrix. The matrix works really well. I hope you guys find a way to use this in your classrooms if you're doing these kind of things, or it's helped me. I hope it helps you. So this is going to be just the math of Ohm's law now. And we'll go 560 times 0.0024 equals 1.344 volts. And you can do the math here. It's probably going to be the same, 1.344. Same voltage, 1.344 volts. Same numbers, same math, same equation, same outcome. And just by looking at these 1.3, 1.3, 2.6, it seems like we're in the neighborhood. And that is the matrix filled out to accomplish this. And we actually even have it available if you want to do pi. You can use power equals current times voltage. And we can figure out watts here as well, and watt total. And that is a quick breakdown of the matrix. I hope it works for you. Thanks, guys. I'm not sure what learning styles we used today in the presentation of the information, and any feedback would be greatly appreciated. Thanks, guys. Having fun. See you in the chats. Later.